In this video, we'll be looking at the second section of the Radioactivity and Nuclear Energy booklet, Ionizing Radiation. Now, this section primarily looks at the three types of ionizing radiation that can be detected through use of a Geiger-Müller tube, often known as the Geiger counter. This will be split into two parts. The first part is absorption. So we have our three forms of radiation here: alpha, beta, and gamma, as shown by their Greek letters here. These three materials represent the different levels of density needed to absorb each type of radiation. So alpha is easily absorbed and blocked by paper, whereas it takes a thin amount of aluminium to block and absorb beta. Gamma rays, however, can pass through all of them and still pass through lead or concrete to a certain degree, but it is reduced, so not entirely blocked. Now, deflection is the next part to look at. Now, this is less well understood at GCSE, but we have our three types of radiation here passing through a magnetic field, as represented by the magnet. Now, alpha particles are shown to deflect upwards. That's just based on the magnetic field in this situation, which will be covered later in the magnetic fields topic anyway. The beta particle, being of opposite charge, at least for beta minus as we're considering it here, is deflected in the opposite way to alpha, but at a larger deflection because it is lighter. Now, gamma has no effect because it has no charge. It has no physical form, so it cannot carry charge. So these opposites and the fact that beta is deflected the most are the relevant factors. Now, this diagram at the bottom shows us the Geiger-Müller tube in its structure, broken down so you can see what happens inside. So we're shown that there is a metal rod with positive charge, an anode, in the center of the tube itself, whereas the outside is the cathode, it's the negatively charged part. We also have a low pressure gas inside the tube that allows interaction with the incoming radiation. Now, as the radiation enters through the thin mica surface, it allows interaction with the particles of the gas. Now, as alpha particles enter, they will be attracted to the negative part. Now, as they move towards the negative part, they'll hit several particles on their way, causing them to become ionized. Similarly, beta would do exactly the same. They would pass in, interact, and themselves be absorbed to the positive metal rod, the anode. Now, during this collision with multiple particles on the way to the charged surface, you end up with a cascade of particles, loads and loads of particles suddenly charged and surging towards the anode or the cathode. This sudden wave causes an electrical pulse. There would not be enough energy transferred for this pulse to be measurable without this cascade. So that allows us to get a count. Now, in this table, we're going to summarize everything we can for alpha, beta, and gamma radiation. Now, to start off with, we obviously have our symbols at the start here. And we need to consider what these are. So the term nature means what is it made of. So an alpha particle is 2 protons and 2 neutrons. Helium nucleus is also acceptable, but I would avoid it because it's very easy to slip up in the exam and say helium atom, which is incorrect. A beta particle is either an electron or its antiparticle, the positron. It depends on if it's beta minus or beta plus decay, which we'll see more about shortly. Now, gamma, fairly straightforward, part of the electromagnetic spectrum. So it is just considered to be an electromagnetic wave. Now that does make it stand out compared to the other two, and in essence makes it easier to work with. So, when we consider the charge, alpha particle has 2 protons, so its charge is plus 2e. You can't say plus 2, it's the electronic charge, so 2 times that value. So it's either 2e or 3.2 times 10 to the minus 19 coulombs. If they ask for an answer with a unit present, they expect 3.2 times 10 to the minus 19. Now, for beta, it is 1e, but it's plus or minus, depending on if it is the positron for plus, minus for electron. And that e value again, 1.6 times 10 to the minus 19 coulombs. Unsurprisingly, with no physical form, there is no charge for the gamma radiation whatsoever. When considering the range in air, what we're actually talking about is how far in air can these radiation forms travel before they are absorbed by particles in the air. So alpha can only reach roughly 5 to 10 centimeters at a maximum, whereas beta will be able to travel 1 to 2 meters. Now, that's the normal safety guideline for doing experiments in the lab with radioactivity. So 2-meter distance, just in case, really. Now, gamma is a tricky one. Technically, its range is infinite, but it does follow something called the inverse square law, which we will look at in a little bit. Now, penetrating power is another term that is used, but what it really means is what will stop the radiation, what will absorb it, what materials can be used. For alpha particles, we know that skin and paper are the 2 thin materials that can be used to absorb radiation. So skin and paper will prevent alpha particles from passing through them, but the alpha particles will be absorbed by that surface. So it's not as though it doesn't harm the skin. Now, approximately 5 millimeters of aluminium will prevent beta particles. That means anything thinner will allow a small amount of aluminium to pass through, which is relevant. For gamma, again, not the easiest one to deal with because it has such a high penetrating power. So it is reduced by, rather than completely being blocked by, either lead or concrete, usually requiring a large amount, such as meters of that material. And even then, some will pass through. So, for magnetic field behavior, we're again referring to that magnet and what will happen to the radiation. So, as we saw in the previous diagram, alpha particles are deflected, and when we refer to beta, we can compare it with this. So for beta particles, we knew that there was a greater deflection. And as well as that, considering this as basic beta minus, we know it would be deflected in the opposite direction. Now, if instead we were dealing with alpha compared to beta plus, they would be in the same direction. So just be careful with that. Gamma, as we've said, has no physical form, therefore carries no charge, so will experience no form of deflection whatsoever. So this is really an easy method of separating the different types of radiation from each other for investigation. So in terms of ionizing effect, what we're really talking about is how likely is it that these types of radiation would cause a particle to become ionized. Now alpha is really high because it has such a large mass. If it collides, it will ionize. Beta, more likely it would pass through the gaps and not interact with atoms. Gamma has a really low likelihood of interacting with matter. And in terms of energy, alpha particles, E equals mc squared, they will have a constant energy. Gamma, running its energy, E equals hf. As long as the frequency is the same, the energy is the same. Beta, it can vary simply because it comes from the nucleus, from a decay. So it can lose energy whilst leaving the atom itself. So there's a maximum amount, but it can lose some on its way there. For the decay equations, just like in the particle physics topic, we will be using very similar symbols, so X and Y for our first element and the one it turns into. A and Z, as usual, represent the atomic mass on the top and the atomic number, so the number of protons, on the bottom. Now in this case, alpha is known to be 2 protons and 2 neutrons, so 4, 2. So the change is -4 to the top number and -2 to the bottom number. Logical. So a good example here, we've got radium, which has been given a 226 as the top number and 88 on the bottom. Remember, the bottom number identifies the element. The top number, the atomic mass, can vary. Now, this is going to decay. You never need to know what the symbols are. These will be given to you. You need to show what the decay particle is, the alpha particle in this case, and what numbers change for the new nucleus. So we have 222, taking 4 away from 226, and 86 after taking 2 from 88. Now beta decay is slightly trickier because you have more particles and you have the 2 versions. So again, we're going to have a change in the nucleus, so X will turn into Y, whatever these elements are. We will also have our beta particle. So starting with beta minus, we could place beta minus with a mass of 0 and a proton number of -1. So that is representing the charge. And it also helps us with the sum itself. Now we know that beta decays will not change the number of things in the nucleus, just the identity. So the number of protons will increase by 1 as an electron is emitted. Now we also get a neutrino. Now compare with the electron or positron. If it's an electron, it's an antineutrino. So for beta minus, it's always the antineutrino. So as an example, let's take easy one like carbon-14. And all that's going to happen is that we will have decay into nitrogen with the beta minus and the antineutrino. We know that nothing changes on the top, so the top value of the mass should be 14. the bottom number should increase by 1 to 7. Now for beta plus, it's ever so slightly different. So again, we can start with our equation of x to y, one element to another. And we can add the beta plus and its associated neutrino. Now, beta plus will have a 0 and a plus 1. And as it's an antiparticle, the neutrino will not be an antiparticle, it will just be a neutrino. Now, as we've got 1 on the bottom of the beta particle, Z must be minus 1 to add up. So as an example, we can look at magnesium, which has been given a mass number of 23 and an atomic number of 12. Now this will decay into sodium, and we'll also have decay products. Now this is what it would look like in the exam already. You would be expected now to add this beta plus, and the neutrino, as well as the mass and atomic number. Now this isn't periodic table knowledge, this is just following the maths, so no change on top, so 23, and the atomic number will decrease by 1 to 11. Now, luckily, that's it for equations, because gamma causes no change to the nucleus. It causes no change to the particles, just the energy present. So any excess energy can be released as gamma rays during or following an alpha or beta decay. So they could be tacked on, but it's unlikely, and it definitely won't appear on its own. However, gamma is covered instead through this. This is the inverse square law. Now, the idea is that instead of particles being represented, we have waves spreading out from a point. So we want to know how many waves are passing through an area, which is represented by its intensity. So if radiation is emitted as gamma in all directions, if you increase your distance from the source, it will decrease how many of those waves actually pass through you. So this law is represented quite simply through this equation. I, for the intensity, is equal to K over R squared. So as we said, I is intensity, and you don't need any unit for this. R, unsurprisingly, is the radius. Now this is the radius of the sphere at which the radiation is being emitted. So essentially it's the same as the distance from the source. K is a constant, an arbitrary value just to make this work, which we usually ignore. Instead, all we really need to care about is the proportional relationship. So we can see that I is inversely proportional to the square of R. So that shows the inverse square law, how radiation decreases as you move further away at a squared rate. Now, another flashback to the particle physics topic is electron capture. This is very much the same as it was in the particle physics topic, but showing that it could come up in the second paper rather than just the first. Now, this occurs when a proton-rich nucleus, so a very positive nucleus, will capture the inner electron so an inner shell, low energy level electron, and pull it into the nucleus. Now, as we know with our quantum numbers, so B, Q, L, etc., this can't just happen on its own. There has to be a balancing factor. So that's why we have our neutrino. You would also get electrons dropping down to fill the gap for the electron that was taken, resulting in further energy being released as gamma rays. So the equation, very simply, we start with our nucleus, and instead of just decaying, we're adding something here. It's absorbing an electron. At which point it will then change into a new nucleus. And as we've added this electron on, that means our value for A will be the same, but Z will have changed. And we would also have to have a lepton to balance out the equation. The only lepton that has no charge is the neutrino, and it's an electron flavor to match the electron that we started with. So our value for A does not change, and Z will decrease by 1. And that's it for this section. Thank you for your time.